Okay, so today we're going to start our units on quantum cryptography. And so we'll start off by considering quantum computing. Okay, so let me just give a little definition of what that means. Okay, so quantum computing, well, basically it's what it sounds like. So it is computation that is based on quantum mechanical systems. Okay, and quantum mechanics is the physics that operates on small scales of space, quantum mechanical systems. Okay, so that means we're going to be dealing with very small systems and maybe encoding information down to the level of a single particle. Okay. And so this gives us really a different model of computation. So different from what's known as classical computation. Okay, and we'll kind of talk a little bit about the differences between the two models at sort of a very low level of information. So why might we be interested in quantum computation? So one big motivation for this, and sort of what set off the whole field, is that there exist efficient algorithms on quantum computers to solve problems that appear to be difficult on classical computers. So there are efficient quantum algorithms for example, integer factorization. Okay, and discrete log problems. Okay, and depending on how much time we have this semester, we may try to gain some insight into how those algorithms work. Now, of course, this may seem like very bad news from our point of view because so such algorithms would basically break every system that we've studied so far this semester. Right? So this would break basically all the public key crypto systems that we've studied. Okay, that wouldn't break everything. Right, so sort of the symmetric systems, so AES, for example, would still be okay. And people are working on developing systems that will be hopefully immune to these quantum attacks. But it's something we have to be aware of, right? So if a scalable quantum computer ever becomes a reality, then really the systems that we've studied all become obsolete. Okay. But on the other hand, it also opens up new possibilities. Okay. However, so there are also protocols so known as quantum key exchange. And so these protocols would allow, well, exactly what it sounds like, would allow you to use a quantum mechanical system for two parties to remotely agree upon a key, which they can then use in a symmetric key crypto system. And so this would sort of obviate the need then for using a public key system to agree upon a key. Okay, so that could accomplish. So this could basically solve the problem that's introduced right by the advent of a quantum computer. Right, we could still be able to securely do remote key exchange. And so even better, these systems are provably secure. So basically, as long as quantum mechanics is correct, so you could prove that it would be impossible for an eavesdropper to break this quantum key exchange. Good. All right. So in subsequent videos, then we'll start looking a little bit at classical computation, sort of on the bit level, and then we'll see how quantum computation is going to differ from that.